to me. Sovereign crown. Okay, it's my crown given to myself for plumbing. Stuff means matter. This comprises the total number of protons, neutrons, and electrons, which in turn determines the mass of the object. Newton's universal theory of gravity asserts that the strength of attraction between two objects is larger for larger mass objects and smaller for smaller mass objects. It also asserts that the strength of attraction is larger for smaller separations between the objects and smaller for larger separations. So, you know, the gravitation force goes as directly with the mass, as in more mass, more gravitational attraction, and goes inversely as the distance between them squared. So it really, really goes up with less distance, and it really, really goes down with more distance, because the distance squared is in the denominator of this force term. It's GMM over R squared, right? So this R squared, the R is the distance between the two objects, and it's squared. So not only is it inversely related to the distance, but it's inversely related to the distance squared. So gravitational attraction really will be much weaker between objects that have more distance than less distance, okay? Feeling quirky. Newton went much further than this qualitative description. So then we just talked about this qualitative, I kind of told you the math one as well, and wrote down equations that quantitatively describe the strength of the gravitational force between two objects. In words, these equations state that the gravitational force between two bodies is proportional to the product of their masses. So as we said, product of the masses, GMM, right? MM as in two M's. One M for one object, another M for another object. And inversely proportional to the square of the distance between them. So GMM over R squared. That's the R squared is the distance between them, okay? This law of gravity can be used to predict the motion of planets and comets around the sun, the moon about the earth, and rockets heading off for planetary explorations, as well as more earthbound applications such as baseballs flying through the air and divers spiraling poolward from springboards. The agreement between the predictions and the actual observed motion of such objects is spectacular. Spectacular. This success gave Newton's theory unequivocal support until the early part of the 20th century. So this law was good for freaking forever. In fact, it's still used. Even now, when we launch rockets and things like that, it's good to just do Newtonian mechanics. It's good to just get the equations and the mass R, all that stuff it's completely okay to still follow Newtonian mechanics, and you will be good enough, right? So that is quite a feat that he gave us some law, some equation so long ago from the 1600s that's still working. So up to the 20th century, it was not only working, it was the law of the land. It was it. That was it. Like nobody knew any better than that. Absolutely nobody. Einstein's discovery of special relativity, however, raised what proved to be an insurmountable obstacle for Newton's theory. So it's not that Einstein came in and said everything about Newton's theory was wrong. It's just that Einstein came in and gave a more general description of gravitation, where Newton's theory is correct for certain sizes, certain speeds and whatnot. After that, we need Einstein's theory, and so Newton's theory kind of becomes a subset of the more updated theory for gravitation, which is general theory of relativity. Okay.